In this video, we are going to discuss about the strange particle that passes through you every second. Take a moment. Look at your hand. It seems solid, doesn't it? A real, tangible part of you. But right now, at this very second, something incredible is happening. Trillions upon trillions of invisible particles are sailing directly through it. They pass through your bones, your skin, your very DNA, as if you weren't there at all. These are neutrinos, the ghosts of the subatomic world. They are not science fiction. They are a fundamental, yet almost undetectable part of our reality. Each tick of the clock brings a fresh cosmic tide of them, washing over you, through you, and continuing on their journey across the cosmos without ever stopping to say hello. Imagine a particle so shy, so elusive, that it can travel through a light year of solid lead without bumping into a single atom. That's the neutrino for you. They are born from the most violent and energetic events the universe has to offer, yet they are the gentlest travelers imaginable. They carry secrets from the heart of dying stars and the fury of the Big Bang, but they interact with so little that catching even one is a monumental achievement for science. Where do these ghostly particles come from? Many are born right in our celestial neighborhood. Our sun, that brilliant ball of fire in the sky, is a colossal neutrino factory. Deep within its core, nuclear fusion reactions are constantly turning hydrogen into helium, releasing tremendous amounts of energy, light, warmth. But for every particle of light created, these same reactions also produce a flood of neutrinos. They escape the sun's dense core in an instant, traveling at nearly the speed of light, while photons of light take thousands of years to struggle their way to the surface. These solar neutrinos are a direct, real-time message from the very heart of our star. But the sun is just one source among many. The universe is a violent and chaotic place, and whenever things get really extreme, neutrinos are made. Think of a massive star, many times larger than our sun, reaching the end of its life. It collapses under its own immense gravity and then explodes in a cataclysmic event called a supernova. In those few brilliant seconds, the supernova can outshine an entire galaxy. That explosion unleashes a blast of neutrinos so powerful it carries away most of the star's dying energy. These neutrinos travel across the cosmos for eons, carrying the story of that star's final, violent moments. Our own planet's atmosphere is another neutrino nursery. Cosmic rays smash into air molecules. High-energy particles called cosmic rays, remnants of ancient stellar explosions, constantly bombard Earth. When they slam into atmospheric nuclei, they create showers, and among that shower are, you guessed it, neutrinos. These atmospheric neutrinos rain down upon the surface of the Earth from all directions. Humanity is not content to simply wait for messages from the cosmos. We are curious. We want to understand the universe's fundamental rules. To do that, we have figured out how to create and control these ghost particles ourselves, right here on Earth. We build magnificent machines called particle accelerators, vast circular tunnels, linear tunnels, where we use powerful magnetic fields and electric fields to accelerate particles like protons to nearly the speed of light. These accelerators are our own, custom-built cosmos in a bottle, allowing us to replicate the high-energy conditions of the early universe or the core of a star. Inside these massive scientific instruments, we take a beam of protons accelerated to incredible energies and slam it into a fixed target, often made of dense material like graphite or beryllium. The collision is a miniature cataclysm, a tiny, controlled explosion that shatters particles and unleashes a torrent of new, exotic ones. Many of these newly created particles are unstable and decay almost instantly into more stable forms. And in that cascade of decay, a pure, focused, and intense beam of neutrinos is born. We can't steer the neutrinos themselves, but we can aim the particles that create them. For example, scientists at Fermilab near Chicago have created a neutrino beam that they aim at a detector in a deep mine in South Dakota, over 800 miles away. There are no tunnels, no pipes, no wires connecting the two. The beam simply travels straight through hundreds of miles of solid rock, mantle, and crust. This gives us an extraordinary power to study neutrino flavor oscillations and their strange properties. The reason neutrinos are so difficult to study is the very same reason they are so fascinating. They barely interact with anything. Think about it. Light is stopped by a wall. Sound is stopped by a door. Your own body is stopped by the floor beneath you. We live in a world defined by interactions, things pushing and pulling on one another. But the neutrino plays by a different set of rules. It is affected by gravity and by the weak nuclear force. And as its name implies, this force is incredibly weak, making a direct interaction with a neutrino an exceptionally rare event. It can miss the tiny nucleus with ease, like a grain of sand thrown through a dozen empty solar systems. This is why trillions of neutrinos can pass through your body every second without you ever feeling a thing. The probability of one of those neutrinos actually hitting one of the atomic nuclei in your body is infinitesimally small. On average, only about one solar neutrino will interact with the atoms in your body over your entire lifetime. You are more likely to win the lottery multiple times than to be knowingly disturbed by a neutrino. Detecting them becomes a game of statistics and immense scale. Scientists build detectors of an almost absurd size to increase the odds of a lucky strike. They fill a gigantic tank deep underground with ultra-pure water or liquid argon and line it with thousands of hypersensitive photomultiplier tubes. They wait patiently, sometimes for years, for that 1 in a trillion interaction. When a neutrino finally strikes, it produces a faint flash of Cherenkov light that the detectors can see, a tiny fleeting sign, a ghost finally caught. So why do we go to such incredible lengths to chase these ghosts? Why build colossal detectors deep underground or powerful accelerators to create particles we can barely see? The answer is simple. Neutrinos are not just cosmic curiosities. They are fundamental keys to unlocking some of the deepest mysteries of the universe. They carry untainted information from the hearts of stars and the chaos of the cosmos. By studying them, we learn about the fabric of reality and our place within it. One of the greatest puzzles is why there is so much more matter than antimatter in the universe. The Big Bang should have created them in equal amounts, yet we live in a cosmos dominated by matter. Some theories suggest neutrinos and their strange behavior could be the reason for this imbalance. We are entering the age of neutrino astronomy. Since neutrinos can travel from the most violent environments without being stopped, they allow us to see places hidden from telescopes. We can peer into the core of our sun or witness a supernova heart in real time. They are a new sense for humanity. In the end, the story of the neutrino is a story of wonder. There is a vast, invisible reality flowing through us at all times, connecting us to the most distant events in space-time. These ghost particles challenge our imagination and push the boundaries of our technology. They are a humble reminder that even the smallest and most elusive things can carry the grandest secrets. The cosmos is speaking to us, and with every neutrino we catch, we learn its language a little better. It's a cosmic lesson in humility, delivered by the quietest particle we know. The quietest and most elusive things can carry the grandest secrets. If you liked it, tap that like and hit subscribe so you don't miss what's next.